Muy buenas a todos los asistentes a este primer Congreso Nacional de Educación STEM. Les agradecemos mucho su asistencia y vamos a tener en este horario de 11 de la mañana a 11:45 una de quizás de las charlas más importantes del Congreso, de un experto en educación STEM, es el doctor Cary Sneider, a quien conozco desde hace más o menos unos 5 años. Ha sido nuestro aporte, aporte académico a todo el trabajo que se ha hecho. Fue una persona que nos ayudó muchísimo en la escritura del libro de Educación STEM, Introducción a una nueva forma de enseñar y aprender, y él nos escribió el prólogo del libro. Para aquellos que ya lo leyeron, estarán de acuerdo conmigo que ha sido uno de los, digamos, de los documentos más inspiradores para empezar en estos temas de educación STEM. El doctor Sneider, para aquellos que no lo conocen, él es astrónomo, él, fue profesor de ciencias naturales de bachillerato, estuvo 2 años trabajando en Costa Rica, aunque nos estaba contando hace un momento que en el tema de los idiomas no es muy bueno, pues tomó clases y demás, pero no tuvo la oportunidad de aprender español. Vamos a tener una dinámica en la que vamos a hablar con él en inglés. Yo les comento primero en español, le traduzco a él los comentarios en inglés, él no responde y luego yo hago una traducción breve. Sin embargo, vamos a tener la oportunidad de que su presentación tenga la subtitulación en español para aquellas personas que de pronto no tengan facilidad con el inglés. Entonces, les agradecemos muchísimo a todos nuestros patrocinadores, especialmente tenemos a Robot School, a TD Robótica, al Colegio Internacional de Educación Integral CIEDI, a ABC Laboratorios y también obviamente a todo el grupo que conforma con STEM, ¿cierto? Que somos Tejer Ideas, STEM Education Colombia, Tejido STEM y la organización TEP. Entonces, demos la bienvenida a Cary. A él no le gusta que le digan doctor. Entonces, it's better to speak to you as Cary, not as doctor, no? You are mute. Wait.
Yes, I prefer Cary.
Cary is better. Le digo yo a Cary que a él no le gusta que le digan doctor Sneider, sino Cary. Es precisamente parte de esa sencillez que lo caracteriza. It is wonderful to have you here live, Cary. That is a dream come true for me, because we are having a long time relationship, and I'm very grateful and all your support that you give to us in writing the book, the first book, and all the comments that you gave us in this development of STEM education in Colombia.
I'm equally delighted to be here and to have an opportunity to collaborate with you over the last several years.
Él está muy contento de haber podido colaborar en los últimos años. Vamos a hablar mucho. Cary nos va a hacer una presentación sobre un aspecto muy importante, que es cómo empezaron los Estados Unidos para abordar la educación STEM de una manera en la que se pudiera volver política pública y que hoy ya tiene un adelanto muy grande, yendo desde las ciencias hacia la educación STEM. Entonces, la presentación de Cary va a ser muy especial, donde nos va a ilustrar sobre el tema. En este momento los estamos viendo a todos ustedes que están en el auditorio, los estamos viendo. Gracias por acompañarnos y pues entonces vamos a empezar. Voy a comentarle un momentico lo que acaba de decir a Cary. Cary, I'll only tell the audience that we will speak about the transition that the United States made,
Yes.
go from the science to STEM education,
Mhm.
and all the difficulties difficulties and the all the steps that is necessary to accomplish to go to have a political or a public policy in relationship to STEM education and the standards. And we will go with your presentation. Carlos, vamos entonces con la presentación. Vamos a empezar.
Greetings from Portland, Oregon. I'm about 4,000 miles away from you right now. When we were starting to plan this program several months ago, I was looking forward to coming to Columbia and meeting all of you personally. Unfortunately, here we are at home, all of us, communicating and spending all day practically on the screen. But it's more than just an inconvenience. My daughter is a nurse. She works in the ICU and she works with COVID patients. I look forward to the time when I can hug her again and my grandchildren. It is a very, very difficult time. As a teacher, I have to say, I see it also as a time for lessons for teachers. When you think about it, the skills that it takes, not just for my daughter who needs to understand the science, the technology of what she's working with, and the ability to solve problems every day. But when we look to the future, when we think about our children, they will be facing very likely not only other epidemics or pandemics, but also issues like climate change, the need to have deal with pollution that is probably going to increase as the global population increases, or the loss of habitat, and so on and so forth. We have to give our children the kinds of skills and knowledge that they will need for the world that they're going to live in. So here in the United States, we are making a change, the change from science to STEM, that I think is absolutely critical for the future of life on the planet. And that's why I'm so honored to be here today, to participate in this program, CONASTEM. So let's get started with a very brief history of this change in the United States. Let's look at the next slide, please. And this shows a very, very quick history of science education reform in the USA on one slide. 1957, I remember going outside with my father. I was 10 years old at the time, and we saw Sputnik going overhead. And I was so excited to see the first space satellite. But a lot of people in my country were very concerned because this was the Cold War, and people were worried about what was then the Soviet Union being more technologically advanced than we were. So that precipitated a political desire to change the education system and produce more engineers and more scientists. And what really started back then, what was launched back then, was a whole sequence of reforms. And today, that culminates in what is now called the Next Generation Science Standards. And I'll be talking about that a little bit. It's not in all 50 states, but it's in 44 states, and the great majority of children now in the United States study in schools where that guides the new science education that is shifting to STEM. Let's look at the next slide, and I'll tell you a little bit more about that. Science education reform really depends on people. It depends on leadership. And we were very fortunate to have Helen Quinn, who was a very well-known high-energy particle physicist, chair a blue panel committee of the National Academy of Sciences to decide what should our standards be. Again, looking at what happened before, what worked, what didn't work, and they came up with what's called the framework for K-12 science education. Although there was only one engineer in that group, one of the important things they did was raise the level of engineering to the same level of science in terms of importance. So just one of the quotes from Helen is to have, you have to engage the students in doing things in order for the learning to become meaningful. So that's a really important idea, and that's one of the themes that you'll see in the next few minutes as I talk about some of the activities to show what it looks like in the classroom. Another leader, so after the framework was developed, then we came to developing the next generation science standards. And our leader in that project was Stephen Pruitt, who has been a chemistry teacher and a leader in education. One of the best leaders I've ever worked for, because he really brought out the best in all of us. And a quote from him is that we don't care what students know. What we care is what they can do with what they know. And that's really the nature and the essence of engineering. Bringing science, bringing mathematics, and bringing an understanding of the engineering design process to a new problem. So let's go on to the next slide, and I'm going to tell you a little bit more about what really STEM is in the next generation science standards. So first of all, of course, as usual, there's science. This is recognizable science: chemistry, physics, earth and space science, biology. And the plans start with kindergarten, although in many states now we have pre-kindergarten plans as well, and they're very carefully developed across the ages. Now, most countries in the world do this. They have a set of standards, and they have often a set of curriculum for that. What's different here from the past is that engineering is at the same level as all the other sciences. And at the high school level, kids are expected to learn 5 different science areas: chemistry, physics, earth and space science, biology, and engineering. Of course, that creates a challenge, but I'm going to get to the challenges a little bit later. I just want to show you first what's expected. So let's go on to the next slide. And so what does technology and engineering look like in the NGSS? So the first point I want to make is, what is technology? If you were to walk down the street and ask somebody, what is technology? At least in this country, they would say, oh, it's computers, or it's my cell phone. Basically, anything that you plug in, they think of as technology. But when you think about it, human ancestors, the Neanderthals, had all sorts of technologies that they developed to survive in their world. So technology is defined as all of the ways that people modify the natural world to meet their needs. So here's the first activity. It doesn't require any materials. It requires observation. Look around you wherever you are right now, and imagine, with this definition, if all the technology were to disappear, what would you see? So I love doing this with kids, because first they'll say, oh, the computer will disappear. Yeah, my cell phone, oops, gone. And I said, well, what else is it that's made by people? And they, oh, the chair I'm sitting on, the table. And then someone also say, well, what do you mean? The whole building is made by people. And when they realize that, and say, well, look, at least my salad from this morning is not going to go away. That grows in the garden. But who planted the garden? So technology, we live in a world in which there's actually very, very little of the natural world around us. You know that the kids really get it when they start giggling, when they realize, okay, clothing is technology. So here we are, standing without any clothes in a woods, or perhaps a marsh, because we don't have any hatchets to chop down trees anymore. We have absolutely nothing that we can use where we've modified the natural world. So the first thing that kids need to understand when studying engineering is, what is technology? Let's go on to the next slide, and the next slide is about what is engineering. So engineering is a process of improving or creating new technologies to solve a problem. It's not simply making things. It is a systematic, creative, and iterative process. By iterative, I mean it's something you do, and typically it doesn't work the first time, so you need to find out what went wrong and do it again, often several times before you really solve the problem. And then once you actually solve the problem, there's the process of optimization. That is, how do you then make it as good a solution as possible? So it's very different from science. In science, you're trying to understand the truth. You're asking questions about either the natural world or the design world, and you need to get to the truth. In engineering, it's very different. You need to solve a problem, and there are many different solutions, some better than others. The process of engineering is trying to find the best possible solution, and it involves generating different ideas, deciding which is the best, modeling, in many cases, computer modeling, but not just that, physical modeling too, testing your ideas and then arguing from evidence about, well, did it work or not? And, or why is this idea better than that idea? So let's go on to the next slide. Now we have a little background of technology and engineering, and I'm going to give you a couple of examples of activities to show what it looks like in the classroom. And we're going to start with a typical science activity, and it involves electromagnets. So I don't know if you've done this before. I've done it many, many times. I used to be a middle school teacher, although I've taught from grades 5 through graduate school. I still think of myself as a middle school teacher. And I love 6th grade especially, because they really cared. Everything I brought them was fun and engaging. Yet they can think like adults. So think of this as a middle school activity. So you take a nail and then you wind wire around it, and you connect the 2 ends of the wire to the 2 terminals of the battery. And lo and behold, you can pick up paper clips. And then the science challenge is, well, what are the variables that affect the strength of the electromagnetic force? I want you to actually make a graph. And, you know, depending on how far it is in the school year, I may tell them how to make the graph. But later in the school year, I'll say, come up with a way of doing it yourself and displaying your evidence. So what usually results is a graph showing that the number of coils of wire around the nail determines how many paper clips it can pick up. More coils means more paper clips. Now, often kids will think, well, maybe we can work together in teams and try 2 batteries. So they find out also that the current makes a difference. So these are the important variables that they find out about through this science experiment. Let's look at the next slide, and I'll show you how to modify this to make it an engineering activity. So I'll start with a slide like the one on the upper right here that shows a commercial electromagnet that's designed to pick up an entire ton of ferric metals. And the idea, these are typically used in salvage yards. And then I'll ask the students, well, look, work with the materials that you have, make some sketches, and try to come up with an electromagnet that picks up as much material as possible. What you find is the kids who are just very carefully making this coil will start and doing all sorts of other things. They'll say, well, what if I bunch up the coil at this end of the nail? Will it pick up more paper clips? What if I use a bigger nail or a different kind of nail? They find out that some, not all steel, in fact, become magnetized. Stainless steel, for example, doesn't become magnetic at all. So they discover a whole lot of other things than from the science experiment alone. And so here's a sketch that's one child made about arranging the materials in a very, very different way, and not just using batteries, but using power from the electrical outlets. I didn't let her do that because it could be a little dangerous. But what they learn is that there are certain, they learn to really define the problem carefully in terms of criteria. In this case, the criterion is pick up as many paper clips as possible. The constraints are you can just use batteries. Also, you can't use more than 2 batteries because there's limitations of the materials. In this case, the wires heat up and you don't want anyone to hurt themselves. So to do engineering, it's not just a matter of making something, it's a matter of being able to first define the problem. So what are the criteria and what are the constraints of this problem? Let's research it further. Let's not just come up with idea, but let's try many different ideas before we decide which one is best. And then we make a model or a prototype, we test it, we learn from our failures, and then we continue to improve. One of the things that's really important about this, it's a process that kids can learn. There are, and it's not a matter of memorizing the steps of the engineering design process. It's, as Helen said, they've got to do this, and they've got to apply their science and apply their mathematics and do this in a number of different ways. Notice, by the way, that this is an integrated STEM activity because it involves the science of electromagnetism, the technology of how to make an electromagnet, and the technology of electricity and the use of batteries. It's the engineering is designing the electromagnet so it is picks up as much metal as possible. And then there's mathematics, collecting the data, graphing, and interpreting the data. This is an activity that's shared between mathematics and science. Let's go on to the next slide. And I want to point out that something about the NGSS is that all instruction is supposed to be three-dimensional. Now, the reason for this, three-dimensional means it takes into account some core idea or a concept related to science, a practice of science or engineering, and a cross-cutting concept. So let me explain what those mean in the context of this activity. So the core idea here is the strength of the electromagnet depends on the current and the distance between two interacting objects. So that's a core idea, and if this were just a science activity, that's the point. Kids learn that, you move on. But there's also a practice, in this case, planning and conducting experiments. When they did the activity to just find out the variables, they were using this practice in the service of science. But when they're doing the activity to test out their ideas to make the strongest magnet possible, that becomes an engineering practice. So conducting experiments can be either science or engineering. But in addition, there is another engineering practice that they were learning about, which is defining and solving problems. They had to identify their criteria and the constraints in order to solve the problem. There's another dimension, a third dimension, called cross-cutting concepts. And this appeared in various versions of standards previously, but it really comes into its own in the NGSS. There are just, I think, 7 of these cross-cutting concepts. What they're for is to show that all the different subjects that kids study in science and engineering are not separate topics. They are of a piece. They represent the way you do science and engineering. In this case, cause and effect. So the cause is the electrical current flowing through the wire creates a magnetic field. And then the structure and function, the way you design and you put together the various pieces, in this case, how you wind the coil, how much coil there is, whether you use 2 batteries or 3 batteries, is the structure and function. In so many different fields, structure and function is important, and you're always looking for causes and effects. Sometimes you find just correlations, and then you do further experiments to understand what is causing what. So let's go on to a very different activity. Let's look at the next slide. And in this one, you think, well, wait a minute, what are we doing? Is this science? Is this engineering? Or is this baking? And the answer is yes, it's all of the above, because baking or cooking involves a kind of technology, the technology we use in the kitchen to transform natural materials into something that we need or we desire. In many cases, some of that transformation took place before the production of flour out of wheat, for example, or corn or other things. But in the kitchen is a wonderful opportunity, especially now during the pandemic. You can assign a project like this where kids' parents can help them. Here's one that I made. This is here's the engineering challenge. You want to make baking powder biscuits. I love baking powder biscuits, and they're very easy to make, which is one of the reasons I love it. But what happens if you don't have any baking powder? And what we're doing these days is we're only going shopping I shop once every 2 weeks. If I forget baking powder and I want to make baking powder biscuits, what do? Well, if I have some baking soda and I have a couple lemons in the refrigerator, I can use that instead, because baking powder is really a combination of an acid and a base, and when you combine them, they produce carbon dioxide. But I can produce carbon dioxide bubbles with baking soda and lemon juice. I can do it with vinegar too, but lemon juice tastes better. So the question is, how much do you put in? Well, you can do an experiment to try to optimize the texture and the flavor of your biscuits. So what this represents is 3 different batches. Now I mixed everything first as I'm supposed to, same amount of baking soda in each batch. Actually, I made 1 batch and then divided it. And each batch now, each third of the batch gets cut into 4 biscuits, but a different amount of lemon juice in each. And then we do a blind test. We bake them all the same. And then my wife comes downstairs and says, okay, which of these 3 tastes better, A, B, or C? And I've got the key over here to know just how much lemon juice I should do. Now, what I love about this is that you can then continue to improve it. I might find out, well, this one is pretty good, but it's not as good as it is with baking powder. How can I modify the recipe further? And so we subscribe to this wonderful magazine called Cooks Illustrated. And in this, there are, for each recipe, there's a description. It's called America's Test Kitchen, how this is developed, that describes the criteria for each new type of recipe. And they describe how they did experiments to improve it and how they finally determine which is the best way, what's the best cookware to use, how best, what temperature you cook it, what ingredients. This is engineering of food. So what are the core ideas, practices, and cross-cutting concepts? In this case, substances react chemically in characteristic ways. This is chemistry. It's also a practice of planning and conducting an experiment. Like with the electromagnet, same practice. So that's an important idea, that those same practices carry over from one type of study to another one. And also they had to define and solve the problem. Again, engineering practice. Very, very similar no matter what you're doing, if you're baking or you're trying to design an electromagnet. But the cross-cutting concepts in this case are a little bit different, energy and matter, because you're working with energy, you're baking these things, you're adding heat energy to it, and stability and change, because things change over time under different conditions with different materials. So, these cross-cutting concepts, again, you can't teach a cross-cutting concept with one activity. But if you keep them in mind during a whole year worth of different activities, then you can see how kids gradually increase their understanding of these over time. That's why all 3 of the dimensions are necessary to teach together. They don't learn a set of concepts now and then later on learn how science is done. They do the science and learn how to apply the science within the constraints and the criteria of a particular situation. So let's go on and let's take a look at the difference in this next one between engineering and science, because this is something that is, let's see, could we look at the next slide? Okay, we'll stop here for a moment. Let me just mention, by the way, one of the things we learned earlier, the difference, a distinction between science and engineering. And then I'll describe these challenges. So for science, there's always a question you're investigating. So scientific inquiry is a process of trying to answer questions. Engineering design is a way of finding solutions. So with science, you begin with questions. In engineering, you begin with challenges. Now, in a sense, in a very important sense, education is a kind of engineering. You're trying to engineer the best possible education for kids. And these are the challenges right now that are facing educators. How do we integrate all three dimensions? Well, in my view, so at the high school level, for example, oh, that's the second one. So a way to do that is to engage kids in activities that are driven by engineering challenges. Typically, kids are much more motivated if there's something they're trying to solve, something they're trying to do, rather than just a question they're trying to answer. And especially if the challenges are related to their own lives, to their lived experiences, or for older kids, to their communities and their needs. So identifying a challenge that's going to motivate them is the way really to integrate the different dimensions. Now, at the high school level, we have 5 subjects: chemistry, physics, biology, earth and space science, and engineering. How do you integrate them when most high schools, in this country at least, require only 3 years of science? Well, the best way to do it is through integrated STEM, to develop entirely different courses that focus on really important issues in the world, whether it's medicine or food production, something that will bring in all of the other sciences together to motivate kids to learn more and perhaps even pursue these fields. And another challenge is that few teachers are comfortable teaching engineering. So the solution, in my view, is ongoing professional development led by teachers. This is I was called into a school district a couple of years ago to lead the revision of their curriculum to bring it to the next generation science standards, and we had teachers teaching teachers. I did the job of facilitating that. I think it was very successful because, again, they were very motivated. If someone says, this is what I do with my 5th graders or my high school students, teachers are much more willing to listen than simply pronouncements by university personnel. Okay, let's go on to the next slide. And I just want to have a few slides at the end to answer the question, why is engineering important for all students? So consider a typical science lesson. The balloon model demonstrates Newton's 3rd law of motion. I don't know how many of you have had a physics class when a physics teacher will blow up a balloon and say, okay, how is this Newton's 3rd law of motion? You let the balloon go, it goes all around the room. The kids laugh, and then you say, okay, well, what was the force, and what was the action, and what was the equal and opposite reaction? Well, the action is the air coming out the back of the balloon, and the reaction was the balloon going forward. And now you go on to something else. But if you're also teaching engineering, let's look at the next slide and see what else you can do. You can say, how can we get our balloon rocket to fly straight or faster? What if we change the materials in the balloon? How will that affect its performance? How can we learn from our balloon model to help us design an actual rocket? So with engineering, you're having students not just learn the concept of Newton's 3rd law, but understanding how to apply that concept in a meaningful framework. All of a sudden, the kids get much more interested, they get much more creative and thoughtful. And that's what you want to have when kids leave you and leave the education system. You really need them to be creative and thoughtful problem solvers. It's what I call an engineering mindset. That means not just ability to solve problems, but the desire to solve problems and to stick with it, to be persistent despite failure. Next slide, please. So another reason why, I've often asked myself, well, why is it now, all of a sudden, after all these years where many teachers have been insisting, no, science is what's important. Engineering is just applied science. So if they learn science and they learn math, they'll find out about engineering later, maybe. Not true. Engineering has its own concepts and skills that are different and go beyond science. And so we can't really wait. Kids should be learning engineering along with their science, both because it's more motivational, but also because they're developing this engineering mindset along with the knowledge of science and math to put things to work. It's also true that in the United States, there are 4 positions in engineering for everyone in science. We teach kids, hey, you can be a scientist. Right. I remember saying that to my kids also. But you know, if you can also be an engineer and actually have a better chance of getting a job. NASA employs 10 engineers for every scientist. I wish I knew that when I was a kid, because I wanted to be a scientist so I could join NASA. I was so thrilled by the idea of sending people into space. But if I had become an engineer, I would have actually had a much better chance to be a scientist. But typically, people become engineers because they already know engineers, someone in their family. We need to have kids understand what engineering is, what engineers do, before they leave for college or any other secondary or tertiary education. So there are also even more jobs for technicians than there are for scientists and engineers put together. So an engineer may have designed this spacesuit, but it's the technicians that built it and maintained it and made sure that the person getting out there in space is safe. So engineering skills are valuable for all jobs, not just for engineering and technicians. Whatever the job is, you will face some kind of problem, something that needs to be solved. And having an engineering mindset will help whatever you do by expanding your horizons to different jobs and also help you in everyday life. So let's look at our last slide. Next slide, please. And this is a quote from the framework, the one that the National Academy of Sciences panel that Helen Quinn chaired to identify a blueprint. And I want you to read this along with me because it's very important, I believe. Many of the challenges that face humanity now and in the future, related, for example, to the environment, energy, and health, require social, political, and economic solutions that must be informed deeply by knowledge of the underlying science and engineering. And that's where we are today, folks. This is an opportunity at this conference to exchange your thoughts and your ideas about how to go about doing that. And I am very honored to have a chance to work with you. I wish I could be there with you, but I'm there in spirit. Thank you very much.
Beautiful presentation, Cary.
Thank you.
That was great. That was great. Una presentación muy bonita por parte de Cary sobre estos temas de los estándares para la próxima generación de los NGSS. Cary, that was beautiful, inspirational. We will see what have to answer the people of the audience. Vamos a ver qué tenemos de preguntas de la audiencia. Tenemos Iván Escobar, dice, how to teach students the risk that a specific technology has. Genetic modification is a patentable technology, therefore life itself is subject to be sold in the market. Please, I want to translate in Spanish. ¿Cómo podemos enseñarle a los estudiantes los riesgos de una tecnología específica? Por ejemplo, la modificación genética y la tecnología patentable, ¿cierto? La vida en sí misma es un asunto de un mercado que se vende. What can you tell us, Cary?
Well, so the question asks about specific technologies. And I want to make the point that, yes, it is important for students to learn about the risk of a given specific technology. But there's a much more important, broader principle here that every technological change will have impacts. Sometimes the impacts can be anticipated, and you want to have an opportunity to think about the problem. So the life cycle, for example, is a part of engineering process where you think about for a new technology or anything that's going to be produced, where do the raw materials come from? What's happening with the transportation? At each step during its use and during its disposal, what are the impacts on people and the environment? But there are also unanticipated side effects, for example, not just for genetic modifications of various technologies, but everything. I mean, look at cars. Who would have thought that cars would kill 50,000 people a year before, or cell phones even? You know, who would have thought people walk into traffic by looking at their cell phone? So it's important to learn this principle that there are both anticipated and unanticipated side effects. And anything that is introduced into the marketplace need to be monitored over time to find out what the problems might be. The genetic modification is a particular one, and I think it's important that students do understand this idea about living things and how you take genes from one living thing, put it into another living thing, what the implications could be. So it's both general and specific.
Ok, voy a tratar de traducir más o menos. Cary nos dice que no es únicamente enfocarse en una tecnología específica, como nos decía Iván, sino hay que en general, hay que dar el mensaje de que todas las tecnologías deben ser generadas, desarrolladas con un cierto grado de prevención, en el sentido de prever qué puede pasar dentro del ciclo de vida de un producto de la tecnología. Adicionalmente, hay que estar atentos a los efectos secundarios que pueden desarrollarse con una tecnología que está entrando nueva en el mercado. Y él dice, por ejemplo, los carros, ¿no? ¿Quién iba a pensar que los carros iban a producir un problema tan complejo como es el tema de la contaminación ambiental? Y lo otro, en general, debe ser visto en mandar el mensaje a los estudiantes de que toda tecnología tiene sus riesgos y tiene sus bondades. Y de aquí en adelante lo que voy a decir es un aporte personal, es definitivamente la T de STEM, pero tiene la intención específica de formar estudiantes en tecnología de una forma profunda, de tal manera que entiendan esto que está hablando, que estaba preguntando Iván, que todas las tecnologías tienen un comienzo, un desarrollo, un final, tienen unos efectos secundarios. Veamos otra pregunta. Carlos, ¿habrá otra pregunta por ahí? No. Cary, I only was... wait. Dice Joe Tao, dice, I think technology doesn't have risk. I mean, we are the ones who use it. It means we are the ones who turn things crazy.
I understand.
Wait, I want to translate to people.
Yes.
Dice, Jotas dice, yo pienso que la tecnología no tiene riesgos. Quiero decir, ¿sí? Que nosotros somos los únicos que las usamos. Y eso significa que nosotros hacemos que las cosas se vuelvan locas. What do you think, Cary?
I understand that the question asker says there's nothing, the technology itself is neutral. It's how we use it that we can use it for good or for bad. However, some technologies have a certain potential, for example, nuclear weapons. And in that case, we have to be very careful. I am a very strong proponent of international agreements to ban nuclear weapons. So we need to be not only scientists and engineers, but as citizens, we also need to understand the dangers of technology and be stewards of technology.
I will try to translate. Cary nos dice que en sí mismo la tecnología es neutral. O sea, eso es el ejemplo que yo siempre doy del martillo. Un martillo está hecho para clavar y puntillas, pero uno puede romperle la cabeza a alguien con un martillo. Eso no lo dijo Cary, lo digo yo. Además, dice él, es cómo la usamos, ¿cierto? Hay tecnologías también que tienen más o menos potencial de ser más peligrosas, por ejemplo, las armas nucleares. Entonces, nosotros como ciudadanos tenemos que ser conscientes de cómo las usamos y aparte de eso, de cómo nosotros en los temas de innovación y el desarrollo de nuevas tecnologías somos conscientes de eso. Carlitos, ¿otra pregunta? ¿Están buscando? Otra pregunta, yo voy a ir traduciéndola. I will translate and you will read it. Eh, ¿Cómo usted recomienda para socializar los conceptos transversales a los estudiantes de la manera que pueda ayudar a generar una perspectiva sobre qué es lo que ellos van a aprender y a aplicar? What do you think, Cary?
So there are two sort of additional cross-cutting concepts that I think are very important here. One of them is simply the information that technology and engineering drive each other forward. They're very much integrated, or engineering and science. You can't do science without an engineer to develop instruments. And you can't do engineering without science to help you understand what are the scientific principles behind what you're trying to accomplish. That's one point. I'll let you translate that, then I'll give the other one.
Okay. Él comenta que hay dos conceptos transversales que son importantes y ya nos contó el primero, que es que tecnología e ingeniería no están aisladas, están íntimamente relacionadas, ¿cierto? Así como también están integradas la ciencia y la ingeniería y también la ciencia y la tecnología. Son temas que deben quedar muy claros para los chicos para que ellos entiendan, ¿cierto? ¿Cómo es que estos dos áreas de conocimiento están integradas? And go on.
And the other point is, ready?
No. You can answer the second
and
one.
the second point is that all technological change affects society. And it's very important as a part of our instruction that our students have examples of the ways that technology affects society. And a lot of students are attracted to become engineers when they realize that that technology is a way of helping society. For example, medical technologies save lives. Technologies for clean water, providing enough food for people, safe transportation. All of these are technological ways to help society. And as the earlier question asker pointed out, it cuts both ways. It can be damaging and it can be
probably this is the last question. Carlos, quizás es la pregunta, pero es la última pregunta, pero voy a tratar de traducir. El segundo, digamos, punto es que los cambios tecnológicos afectan a la sociedad, ¿cierto? Y hay que ilustrar a los estudiantes con muchos ejemplos, ¿cierto? Especialmente que la tecnología tiene el objetivo de ayudar a la gente, ¿cierto? Y, por ejemplo, para salvar vidas en el área médica o tener transporte seguro. Entonces, ese mensaje debe ser enviado también a los estudiantes como un concepto transversal. Yo creo que hasta aquí vamos a despedir a Cary porque ya la agenda no perdona. Nos quedan 10 minutos para las 12, ahorita tenemos nuestra segunda parte. Cary, I want to thank you a lot because your presentation was very beautiful and the answer was very clear. The agenda is tight. We need to go on. We have a next panel
Yes.
presentation at 12 o'clock here in Colombia. Your participation was great. Thanks for your collaboration.
The pleasure was all mine. I enjoyed being here, and I very much hope that when we have CONESTEM 2, I'll be there in person and can meet everybody.
Nos dice Cary que está muy contento y que ojalá que cuando tengamos un segundo congreso de educación STEM, él va a estar con nosotros en forma presencial. Cuéntalo, Cary.
Hasta luego, amigos.
Excuse me. Thank you for this clear explanation of classroom practice about the STEM education. It's an honor to be able to witness the education transformation in Colombia. En este cierre les recomendamos por favor a todos los que nos están viendo que en la descripción del video encuentran el enlace de asistencia y evaluación de las ponencias de cada una de las sesiones en las que hemos estado. Así que por favor no olviden completar esos registros que son indispensables para la toma de asistencia y para evaluar en general el evento. Thank you so much, Cary.
You're welcome.
Bye bye.
Con mucho gusto.